So for question 10 and 11, there's basically one idea at play. It's the Isosceles triangle theorem and its inverse. Um, the idea is that if you have an isosceles triangle, then so it's like if you have an isosceles triangle, then the base angles of it, those angles that are across from the congruent sides, must be congruent. Right? That's the idea. But the converse is also true. If you have a triangle in which you've got two congruent angles, then the sides across from those angles must also be congruent. So when I look at this problem, because I see that I've got a pair of congruent angles here, I know that the sides across from them, right, must be congruent as well. So because these sides are congruent, by definition they have to be equal in length. So finding x is pretty simple here, right? It's just a matter of writing this equation that states that 3x minus 19 is the same thing as x plus 5. I can take away an x from both sides, get 2x minus 19 is 5, and then I can add a 19 to both sides. 2x is equal to 24, positive 24. And if I divide both sides by 2, I get that x is 12. So this is 12. For the other, because this is an isosceles triangle, right, these are marked congruent. Because of that congruency, I know that these base angles must be equal to each other. And at first glance, that may be like, well, how's that going to help? Well, if we apply the triangle sum theorem as well, we could write x plus y equals 112. So x plus y equals 100. I'm sorry. The three angles x, y, and 112 in any triangle add up to 180 degrees. Now, because x and y are congruent to each other because of the inverse of the triangle isosceles triangle theorem, we know that x and y are the same angle. So I could easily replace this y with x because it's equivalent to x. And if I do that, this can be rewritten as 2 of the x's, right, plus 112 equals 180. If I take away 112 from both sides, we get 68. So 2x is 68, therefore x would have to be 30. This is 68, therefore x would be 34. And if x is 34, y is 34. So both x and y are the number 34. Let's go down to question 13 and 14. Just a bit of vocabulary, right? Complementary angles are angles that have a sum of 90 degrees. When I add them up, I get 90. And supplementary angles are angles that have a sum of 180 degrees. So when I add these up, I have to get 90 for the complement, and I have to get 180 for the supplement. So if I'm thinking about this, there's some angle 23 plus some angle I don't know, and that has to equal 90. So you can see by taking away 23 from both sides, we get x, and x would have to be 67 degrees. And you can verify that, 67 plus 23 should be 90. For the supplement of this angle, right, we understand that 23 plus some angle, I'll call it y now, that I don't know, they have to add up to 180. So if I take 180 and I subtract the 23, I get that this y has to equal 157. So complements and supplements. Same thing over here. I don't really need to write all of this out, but I will. If I add them up, I get 90. Therefore, x is just a 1. If I add them up for the supplements, plus some angle y, I get 180. If I take 180 and subtract 89, I'm looking at 91. So y equals 91 degrees. So there we are. The complement of 89 is 1 degree. The supplement of 89 is 91 degrees. Let's move along. So for question 15, we're told that we're given two sides of a triangle, and we're asked for the possible length of the third side of each of those triangles. So to demonstrate this, I put together a quick sketch in GeoGebra. Notice that we're starting here. We've got a 12 centimeter and an 8 centimeter side lengths. For my demonstration, I've done 12 and 4, so just so you can see how this is working. So if I have 12 and 4 next to each other, you can see that that adds up to 16, but it's not making a triangle. So here's the thing: if the third side equaled 16, it would not make a triangle. What it would make would be a line like this, right? So it can't be 16. And in fact, it can't be greater than 16 either. We don't get a triangle until this third side starts to be less than 16. So here's this third side, and again, I could ask GeoGebra to figure out what the measurement of that size is. So let me go to its object properties, and under style, I'm going to ask for its value. So, oops, there was a label I was turning on, so let me show that label. And actually, let me go back and modify the label so that it will show me its value. So there we go. So you can see right now the side length is 15.05. So if the side is 15.05, you definitely have a triangle. But notice that if I bring it up here, the largest I can make this is 16. And when that third side equals 16, I don't have a triangle. I don't have a triangle at all. What I've got right now is just two line segments. They're both 16 long. One of them is 12 plus 4, and the other one is 16. Now, as soon as it's less than 16, right, this is all a triangle. In fact, everything less than 16 is a triangle until you get way over here where they come back together. And then right here you can see, oh, it's no longer a triangle. Right now it's just a line segment again. One is 8 long. And the other is 8 long. They're both 8. And again, why are they 8? Well, because now this 4 is being subtracted from the 12. So 12 minus 4 is 8. So there's no triangle there. So this third side, right, are all the values that are less than 16 but greater than the number 8. And that's how we would write it, right? The third side is anything greater than the difference between the numbers, but less than the sum of the numbers. So if we come back to our problem here, when we look at the 12 and 8, if x is the length of the third side, x could be anything that's greater than the difference between those two. So it has to be bigger than 4, but it has to be less than 20. And again, you can see what I'm doing here is I'm just taking 12 minus 8, the difference in the numbers, that's giving me my lower bound, and 12 plus 8 is giving me the upper bound. So all of these values of x would form a triangle as long as x is in that range. If x is greater than 20, forget about it. And if x is if it's less than 4, forget about it. It's not a triangle. If I come look at this, same thing, right? So again, if x is my third side, there's a range. The lower bound is the difference in these numbers, so I'm taking the 25 and I'm subtracting 11, and it shouldn't be much of a surprise. I'm writing down 14. And when I put those together, I get 36. So as long as x is in between those, it can't be the endpoints. It can't be 14 and it can't be 36. But as long as it's in between 14 and 36, that third side would allow us to form a triangle. Let's move along here. What is the longest and shortest side of the triangle? So in a triangle, in a single triangle, it is the fact that the longest side is across from the largest angle, and the shortest side is across from the shortest angle. Now for this particular triangle, I probably should know what this angle is before I make the pronouncement about which one's the largest side and which is the smallest side. So in order to get this, I understand that these three angles have a sum of 180, so 40 plus 112 plus some angle k that I don't know is 180. So all I'm doing is I'm taking 180 and I'm subtracting 40 and I'm subtracting 112. And when I do that, I get that this angle K is 28 degrees. Well, the problem cautions us that this drawing is not drawn to scale, and it's really clear it is not drawn to scale because this side would have to be the smallest side. Oops. Write that. So the smallest side is side MN, or segment MN, and the largest side is the one that's across from the 112. So over here is the largest.